Hi, Miriam. Hi, Rebecca.
Good morning. Can you hear me?
I can hear you.
Okay, good. I switched headphones.
Okay. Oh, did you
My-
steal your daughter's bag?
I did. I have a cute little turquoise pair of Beats. So they have now been recuperated. Of course, she has AirPods, so she doesn't care about these things anymore. These have a wire. So, well, good. Okay. I was wondering.
Morning, Adam.
Good morning. I go get coffee. I need it.
Okay. All right, it's 10 a.m. We'll go ahead and get started. I'm going to talk about two questions today and show you what they look like on test 3. We've got the redox question, redox balancing question, and then this direction of flow problem where we have to figure out what arrow goes with what property of the galvanic cell. But I'll start off with the redox reactions. And I'll first of all outline the steps here that we need to go through in order to solve this. All right, so step 1 is write out the half reactions. I'm just going to do this in fairly abbreviated form because You've already got all this on the videos and also in the PowerPoints as well. The next thing, balance the elements being oxidized or reduced. Actually, I might put these on so you can hear me a bit better. There we go. And what we're talking about here are the elements that usually are not hydrogen and oxygen. So not H or O here. Then we need to balance O, and we do that by adding water. Then we balance the H. And we do that by adding H+. Then we balance the electrons. And then we multiply to get rid of the electrons.
Quick question.
Yeah.
Oxidation, it loses electrons, and reduction, it gains, like, or vice versa.
No, that's right. But it comes down to where the electrons are in the reaction equation. If we're saying something's losing electrons, it means electrons are products. If something's gaining electrons, it means the electrons are reactants. So we'll see that when we go ahead and do this. And then we can balance for base at the end of that. Okay, so for something like this, I'll just go through all the steps here. Can't help but think I've missed something, but we'll see that as we go, I hope. So if we're looking at half reactions here, we'll do S2O8 2-, and that's going to give SO3 2-. And the element being reduced or oxidized here, we don't know which yet, is going to be the sulfur. So that's why I've chosen those two specific things as being part of that half reaction. The other one here is Cl2 goes to ClO3-. And that's going to be the other half reaction. So that's step one done. The next thing we do is we balance the elements being oxidized or reduced. In this case, it's sulfur and chlorine. And those are usually not hydrogen or oxygen. So it's usually pretty easy to tell what's being oxidized or reduced here. So the way I would balance that is to put a 2 in front of here. And I had to balance this one as well, put a 2 in front of here. So I'll stop there for a second. Does anybody have any questions about what I've done so far? Let's have a little more room here. Okay. So the next thing, sorry.
Are the oxygens in this case balanced or no?
Not yet, but I'm just about to do that.
Okay.
So I'm looking at it and I see the oxygens here, there's 8 on this side, but there's 6 on this side. So no, the oxygens aren't balanced. The way I would balance them then is to add water, and I'll add 2 waters. Now the oxygens, the number of oxygens I add will always be as many waters as are needed to balance out those oxygens. So if we had 8 on one side, 6 on the other, that means I'll need 2 on this side, on the right-hand side, and that means 2 waters added to the right-hand side. So I'll stop there for a second. Does anybody have any questions?
Nope, I just caught up.
Okay, so the bottom one here, we got 2 times 3, that's 6 waters. So we need 6 sorry, 6 oxygens. That means we need 6 waters on this side. That's an oft-made mistake there, is not including the coefficient there, thinking there were only 3 waters when there were actually 6 needed to be added. Any questions so far? So the next step is to balance the hydrogens, and we do that by adding H+. I'm looking over here, I see this one has 4 hydrogens, so I'm going to go ahead and add 4 H+ over here. And for this one is going to be 12 hydrogens, so I'll add 12 H+ over here. Any questions so far?
Yeah, so what gets oxidized and reduced at this point?
Well, I'm not going to say anything until we put the electrons in, Adam, and then we'll be able to know for sure.
All right.
But I mean, I can tell you on a somewhat intuitive basis, and what I can say is that if you're looking at the bottom one, the chlorine, you can see that when we're going from the reactants to the products, we're clearly adding oxygen, right?
Right.
Right. So that would be definitely an oxidation. If that's an oxidation, the other one definitely has to be a reduction. I can kind of get an idea of that too, because you've got 8 oxygens going to 6. So a decrease in oxygens is usually a reduction. An increase in oxygens is usually oxidation.
Okay.
Is that necessary to know right now? Not really, but you know, it is. It's there.
Okay.
Okay, the next thing we need to do is add in the electrons in order to make sure that this balances. Now this is a little bit tricky. So, you know, you got to be, this is where people usually make their mistakes with the balancing, is by adding the electrons. So the idea here is that you need to figure out the total charge on each side of the reactions. And I can say on this side, we've got a total of +2.
Mm-hmm.
And on this side, we've got a total of -4. So the idea is that you look at the difference between the two, and that's the number of electrons you add. And the rule is you always add electrons to the side that has the higher charge. So a common mistake that people will make here is they'll say the difference between +2 and -4 is 2, but it's not, it's 6. So it's actually 6 electrons, and they get added to this side. So what I was saying earlier, Adam, is that's a reduction because the electrons are on the reactant side.
Wait, 6 electrons? I mean, like, I understand how you got the +2 because there's four positive charges for hydrogen or hydronium. But where does the 6 come from?
I'm telling you right now. I've probably reversed this, but it doesn't really matter. But
Yeah.
if you put these on a number line, you can see it goes, the difference is 6. Think of it this way.
Okay, yeah.
All right. But the rule is find the difference between the two sides in charge, and then add that to the other side. The side, the side that has the higher charge on it. So +2 gets the side with +2 gets the 6 electrons.
Okay.
Now on the bottom, we've got 0. And what I can tell you is that if something doesn't have a charge on it, always assume it's 0. So water and Cl2 here, they're both 0. Now on the other side, we've got a total of +8. So we'd add 8 electrons to that side.
That's not 10.
No, I don't think so. Hang on. Oh, you're right. I was just testing you.
Okay, I appreciate that.
Let's try that. Okay. Now that's plus 10. There we go. There we go. That's better. Plus 10. So minus 2 plus 12 is 10.
Nice.
All right. Any questions? I think we're good now. All right. So that's balancing the electrons. The next thing we need to do is multiply to remove the electrons. Now we've got 6 and 10. You might say, well, let's just multiply the top one by 10 and the bottom one by 6 and call it a day. But that's not the smallest possible thing that we could use in order to do that. I often compare this process to that when you're trying to add fractions and you're looking for the lowest common denominator. You're kind of looking for the lowest possible things to multiply these by. So for this one, it would be 30 would be the number I'd be aiming for. So I would have to multiply the top one by 5 and the bottom one by 3. And, you know, it's whatever it takes to get rid of those electrons, really.
Is it just to get like just a whole balance of just same amount of electrons?
Well, the whole point with the redox process is that something's giving up electrons and something's taking them. In this case, it's the bottom reaction that's giving them away and the top reaction that's actually accepting them. Because the bottom reaction is the oxidation and the top reaction is the reduction.
Mm-hmm.
But the trick here is that it's got to be the same number of electrons transferred. So the number of electrons given away has to be equal to the number of electrons being received.
Okay.
So given that, I could see, I always like to handle the H pluses first because and the waters because they're the most difficult. So let's look at the H pluses. Over here, I see I've got 20 and down here, I've got 36. So that would be 16 H pluses on this side. So I'll stop there for a second and make sure you understand how I got that 16 H plus. Does anybody have any questions about that?
Man, you added the hydroniums together, or?
Well, I had 20 H pluses on the top, 5 times 4. And on the bottom, I had 36, but they were on the other side. So treat the arrow like an equal sign. So we have 20 H pluses on one side, 36 on the other. That's 3 times 12. 36 minus 20 is 16.
And is there a reason we put them on the product side and not the reactant side?
Because you have 20 on the reactant side and 36 on the product side.
So it goes on the one with the larger.
Yeah. It's just like if you had a mathematical equation. Let's say you had A plus 3B equals 6B plus D, right? And you wanted to combine the like terms, you'd subtract 3B from each side, right? So you now have 3B on the right side.
The right side.
Yeah, you with me? So just treat it like a combining terms type situation as you do in math. And you can see that it's not going to be that difficult if we do it that way. So
it's going to be products minus reactants.
Well, not necessarily. It's whatever has the highest thing.
Oh, okay.
So you got 20 and 36. So it'll go on the side with the higher amount. Now the other one, we got 18 and 10. So that'll be 8 H2O, but that'll go on this side. So 3 times 6 is 18. That's right here. And then the, let's see, over here we've got 5 times 2. So that's going to be 10. So that's why we're left with 8 on the reactant side. Any questions? Now the other ones, because it says they only have one instance of each, they're a bit easier. So we've got 5 S2O8s over here. 5 S2O8, 2 minus. And then we've got, let's see, what else have we got? We've got 3 Cl2s as well over on this side. And over here we'll have 10 SO3 2 minus, that's 5 times 2. And down here we'll have 6 ClO3 minus. Now hopefully that should be balanced. Does anybody have any questions so far? Now we actually can definitively determine if this is right, because if it is correct, then we're going to have the same number of elements and the same charges on each side of the process. And we can actually check on that and make sure that we're right. So you can see that we've got 3 Cl2s, that's 6 Cls, and on the other side we've got 6 Cls, so they're okay. We've got 10 sulfur on the left, 5 times 2, and then we've got 10 sulfur on the right, so that's okay. Oxygens, we've got 5 times 8 is 40, plus 8 is 48. So that's 5 times 8 is 40, plus 8 is 48. That includes the waters, the oxygens from the water here. On the other side, we've got 10 times 3 is 30, 6 times 3 is 18, 30 plus 18 is 48. So the oxygens are okay. The charges, we've got 2 times negative 5 times negative 2, that's negative 10. And on this side, we've got 16 minus 20 minus 6. And that's going to be negative 10 as well. So we know that this is completely balanced. Does anybody have any questions? Okay, I'm going to take off some of this, not all of it.
I go away for a bit.
All right. Okay, so that's balanced for what we call acid because we got H plus in there. Now we're going to look at how we might balance for base. And what I would do with that is I would add 16 OH minuses to both sides. And it's always adding, it's like kind of like you're titrating. So you've got 16 H pluses, so you know you have to add 16 OH minuses to each side. Now if we do that, the H pluses and the OH minuses combine together, and that gives us water. It'll be 16 waters. And then if we fix that, we'll have we'll have 8 waters on this side, and then the other things added as well. All right, does anybody have any questions? So that'll be balanced as well, but that's balanced for base because now you've got OH minus in there.
So just to be positive, you subtracted the 8 H2O from the left side from the right?
Well, I had 16 on the right and 8 on the left. So that would leave me with 8 on the right.
Okay.
All right, any questions? Any questions about this? Okay. Let's take a look at the kinds of things you're going to see on the practice test. Now, there's a couple of possibilities of problems here. That's why I'm going to try and do a couple of attempts here, so you can see the different possible kinds of problems that you could get here. All right. Let's we'll do this one as an example first. I'll leave the steps up here. But we're just going to be following the same kinds of rules. So we've got XO3, and I'll just do the half reactions first. We'll do XO3 minus 3. In this case, it's the X and the Q that are going to be oxidized and reduced. Okay, so XO3 3 minus, or minus 3 goes to X2 1 plus. And the other one is QH8O gives QH6O2. Okay, any questions so far about the half reactions, figuring out the half reactions? All right, the next thing we need to do is balance the elements being oxidized or reduced, and that means putting a 2 in front of the X here. Any questions so far? And on the, excuse me, in the case of the other one, we've got Q and Q, that's just going to be 1 and 1, so that's okay. The next thing we do is balance the oxygens, and we've got 6 on this side, so we add 6 waters over here. And for this one, we've got 1 oxygen, 2 oxygens, so add 1 water on this side. All right. Any questions? Sorry. Okay, the next thing we'll do is balance the hydrogens, and here we've got 0 hydrogens over here, we've got 12 over here, so I put 12H plus. I'll move that over a little bit. Okay. And on the bottom one, I've got 8 hydrogens on one side and 6 on the other. So I'll add, no, more than that. We've got 8 and 2 is 10 and 6. So that would be, that'd be 4H plus over here. So that's something you've got to be careful of. Make sure you include the hydrogens of the water as well. Any questions? Nobody's saying anything. Everybody's fine with that, huh? All right. All right, well, okay, I'd like some feedback here. Let's see. How many electrons are going to need to be added to the top reaction, and on which side do they go?
I'm back.
Okay. All right, so anybody want to take a punt here? Take a guess?
Hold on.
So the charge on the reactant sides of the first one would be +6, correct?
It would. And what's the charge on the charge on the product side of the first one?
Would it just be +1?
Yes, that's right. So what's the difference between plus 6, and plus 1?
Just 5.
5. So then that'll go on the side that has a higher charge. And there we go. Now the bottom one's fairly easy. That's just going to be 4 electrons because there's nothing on that side. There's plus 4 on this side. So we need 4 electrons on that side. Any questions? All right, so the only way that we can make this work for the electrons is we can multiply the top one by 4 and the bottom one by 5. And then we can go through the same process as we did earlier. So the electrons are definitely going to cancel. Now we're looking at the H pluses. All right, does anybody want to tell me how many H pluses there are going to be and on which side they're going to be?
It's going to be on the reactant side.
Okay, and how many?
28.
18.
28.
Yeah.
Yeah. 4 times 12 is 48. I think somebody, was that you, Miriam, who said?
Yeah, 28.
Yeah, 28. So it'd be 48 minus 20. That's 5 times 4. So that would be 28 H plus on this side. Okay. Now the H2Os, let's see. How many H2Os?
Wait, what's the Q?
19 on product side.
Yeah, 19. What was that?
What's Q?
Doesn't matter.
Okay.
Q is just one of the elements that's being oxidized or reduced here. In this case, it's being oxidized. Yeah, 19 is right. So 24 on top, 4 times 6. 5 times H2O on the bottom. 24 minus 5 is 19. So that's where we're getting the 19 from. Anybody got any questions? All right, so we'll fix up the rest of this. So that'll be 8 XO3 minus 3, or 3 minus, plus 5 QH8O. And then over here, we'll have, let's see, 4X21 plus, and then 5QH6O2. There we go. All right, so that should be balanced, and we should check on that to make sure it is, and we can check on it. Let's check out the X's first. So 8X on the left side. On the right side, 4 times 2, that's 8. So X is okay. Oxygens, we have 24 plus 5 is 29. 29 oxygens on the left side. On the right side, oh, hang on. Yeah, that's all right. And on the right side, we have 19 times 1 plus 5 times 2. 19 plus 10 is 29, so the oxygens are okay. The Qs, there are 5 Qs, 5 Qs, so they're okay. Hydrogens, we have 40 plus 28, that's 68. And on the other side, we've got 38 plus 30, that's 68. So the hydrogens are okay. The charges, we've got negative 24 plus 28, that's plus 4. And on the other side, we've got 4 times 1, that's plus 4. So everything balances out here. So we know that that must be right. So the answer here is going to be the sum of all of these, which would be 8 plus 5 is 13, plus 21 is plus 28 is 41. 41 plus 19 is 60. 64, 69. So the answer there would be 69. Does anybody have any? Sorry? Adam?
Because that's just the overall coefficients.
Yeah, that's right. The 8, the 5, the 28, the 19, the 4, and the 5.
All right.
Just add them all up. If you've balanced it correctly, then you'll get that same answer. If you've balanced it incorrectly, obviously it'll be wrong.
All right.
Just for the purpose of practice, could you balance this for basic conditions?
It would be to add 28 OH minus to this side, and I'll add 28 OH minus to that side. So that would be 28 waters on the left, and that's 28 minus 19, so that would be 9. So you have 9 waters left on this side. So the balance for base would look like this. What did I say? 9.
And why is the 9 on the reactant side instead of the product side? Oh,
Because it's 28 minus 19. And the 28 is on the...
yeah.
You with me?
Yeah.
Okay.
And why did we add hydroxide to it?
Because I was asked to. I was asked to do it for balance it for base, just for kicks. But you're not required to do that for the question, Adam.
Okay. Oh, okay. Okay.
All right. Anybody got any questions about this?
No. I'll ask whenever this session's done.
Okay, but you had nothing specific about this one, Adam?
I missed out on half reactions because I had to use the restroom.
Okay, well, the half reactions is just whatever involves the X and whatever involves the Q. So there's X and Q and Q. That makes up our half reactions. And that's it.
I don't get it.
Okay, we'll talk about it after. We'll talk about it afterwards, Adam. All right. Let me see. I'll submit the quiz here. No, I want to submit the quiz. Let's see. I'll move this down here. That's what I'll do. So I wanted to just do another example here. Let's see if I can pick up the other kind of example that you could possibly see. Otherwise, I'll keep on doing this until... All right, let's have a look. Here we go. This is the other kind. So actually, Adam, this will help you to see how we get the half reactions on this one. So we'll have, for this one, the half reactions would be XO3 -2 plus, oops, not plus, gives XO2 minus, and the other one is going to be Y23 plus, gives YO2 plus. Is that clear, Adam? How I'm getting the half reactions out of that? I'm just picking out the X's and the Y's, that's all. So the one that involves the X's That's one half reaction. The one that involves the Ys, that's the other half reaction.
I don't understand.
Can I ask what you don't understand about it?
Something about the X and Y.
The X and Y aren't real, right? They could be any element. But
so what makes it a half reaction? Like,
well, the full reaction involves X's and Y's. The half reactions break it down so we can see what's being oxidized and what's being reduced.
oh, okay.
Now, at the present time, I can look at it and I can say, well, it looks like the top one's a reduction. I can say that because there's more oxygen on the reactant side than the product side. So it goes down from 3 to 1. And the other one goes from 0 to 1O. So I'm pretty sure that's an oxidation. But in any case, you're always going to get one oxidation, one reduction.
Right. So the XO3 is being oxidized to XO, and then the Y2 is being reduced to YO2 or YO.
Well, yeah, YO, but with charges on them too. So XO3 minus 2 is being reduced to XO minus 2, and Y23 plus is being oxidized to YO2 plus.
But all right, so whenever we're referring it to reduction and oxidation, like I know reduction, it's basically gaining electrons, but at this point it's not really gaining any electrons.
It will. We'll get there, right? We'll see that in a second, okay?
Yeah.
Okay, so let's move on to the next part. We need to balance the elements, not balance the elements being oxidized or reduced, which means that we're balancing the X's and the Y's. So the X's in the first one are already balanced because that's going from 1X to 1X. On the bottom one, it's going from Y2 to 2Y. So I need to put a 2 in front of that Y. Any questions? Okay, the next thing, we balance the oxygens. We do that by adding water. On the top reaction, I've got 3 on the left. I've got 1 on the right. I'm going to have to add 2 waters.
Right.
And on the other one, I've got 2 oxygens there, so I need to add 2 waters down there as well, but on the other side. Get a little bit clearer. There we go. Any questions? All right, now we're going to look at the hydrogens, and on the top one, I've got 4 hydrogens, which means I have to add 4 H pluses on this side. And on the bottom one, I've got 4 hydrogens there as well. So I add 4 H pluses on that one as well. Okay. Any questions so far? All right, the next thing, yeah, go on.
Yeah. You got the 4 plus hydronium by looking at the second one first.
Well, I'm looking at
you balanced it, all right.
Yeah, well, there was 2 H2O, so that's 4 H's. So I need 4 H pluses.
When did you put the 2 in front of the H2O?
Well, because of the 2 O's here, that means there was 2 waters. See, 2O, 2.
Yeah.
That means I need 2 waters.
Okay.
That's where that comes from. Is that all right?
Sure.
Now, the next thing is the electrons. So let's see if anybody can figure out the electrons here for this one. So go ahead and look at it. See if you can see.
All right.
So what do you think for for the top one, Adam?
The reactants is going to have a +2. And then
Okay.
the products is going to have a 2 minus.
Mm-hmm. So how many electrons are we going to add?
Hold on. We have +2, 4.
Yeah,
Four
to which
electrons.
side? Left or right?
Left.
There we go. Now for the other one, what's it going to be on the bottom one?
3+ reactants, and then 2+ on products. Oh wait,
No.
wait. 6+.
No, not 6+ either.
8+.
8+, yeah. So how many electrons?
Is this where I like start balancing them out? Or actually no, 5 electrons on the right.
Yep. Me. Yes, 5 electrons on the
Okay.
right. There we go.
All right. All right. I'm just gonna start balancing this out.
Okay. So anybody got any questions so far? Okay, let's look at the number of H pluses we're going to have. So how many H pluses are we going to have? And which side are they going to be on?
Well, hold on. I just got tripped up. The 5 and the 4, the multiplier, which one are we trying to like balance out more?
Well, we got 4 electrons on the top reaction, we got 5 on the bottom. So the only way that we can even those out is to make it 20, 4 times 5. So that's why I multiplied top one by 5 and the bottom one by 4.
Okay. All right. Okay, so for the top we're gonna have 20 hydroniums, and then for the bottom we're gonna have 16.
Mm-hmm.
So there's gonna be 4 hydroniums on the reactant side.
Right. And what about waters?
Top one has 10 water, and then the bottom has 8. So there's gonna be 2
That's right.
on the products.
That's right. All right, so now we can put the rest of it in here. So it'll be 5xO3 2 minus plus 4y 2 3 plus, and down here 5xO2 minus, and then 8YO2 plus. Okay. So we'll make sure that that's all balanced. So we've got 5 X's and 5 X's, so that's okay. Oxygens, we got 15 on the left, and on the right we've got 2 plus 5 is 7 and 8 is 15. So the oxygens are okay. Y's, we have 8 and 8. That's good. And hydrogens, we've got 4 and 4. So they're okay. Charges, -10 plus 12 is 2 plus 4 is 6. So 6 on the left, and on the right we've got -10 plus 16, that's 6. So it must be right. So the total there on the coefficients, 5 and 4 is 9, and 4 is 13, and 2 is 15, and 5 is 20, and 8 is 28. So the answer would be 28.
For the charges, right?
Mhm.
So we have okay, all right. All right. So that's just the overall charge on the equation.
Well, 6 and 6, it equals each other on each side. And it should if
Okay.
it's balanced, yeah. And you can look at that and you can see the top one is a reduction, the bottom one's an oxidation, and then I can tell that by the electrons. The electrons
Right.
are on the reactant side on top one, they're on the product side on the bottom one.
And if we're doing it, if we're balancing for a base, is that the correct terminology? So we add 4 hydroxide to the reactant side,
Yep,
and then 4 over to the other side as well.
that's right.
So we get 6 water on the product side, or
Yeah, that's
am I
right.
done?
Yep, that's right.
Oh, on the reactant side. Huh. Wait.
Well, it would have been 8, right?
I just kind of guessed in a way.
All right. So, oh, sorry, 4. I'm sorry. No, it should be 2.
Should be 2.
Yeah, I'm sorry. I got caught up in that. I got caught up in your guess, Adam.
Because there's 4 and then minus 2 and then 2. Okay. Yeah.
Yeah, so it should be 2.
Yeah. Okay,
All right.
that's cool. Good stuff.
All right. Any questions? So those are the only 2 kinds of questions you're going to see. So you got plenty of practice on those. You can just keep on doing them.
Excuse me.
All right. Does anybody have any questions? Any other questions about the redox balancing? Okay. All right. Let's move on to the next part here, and we'll go back. Let me show you the key. Okay. All right. So the idea here is you've got this setup, and what varies is W, X, Y, and Z. This is actually pretty similar to what you'd be doing on the test as well. The W here is a metal bar that is immersed in a solution of an ion of that metal. So zinc in this case, and then zinc 2 plus will be the X solution. So that X is a solution there, an aqueous solution. Y is cadmium, cadmium 2 plus, and Z is cadmium metal itself that's in a solution of cadmium 2 plus. Between the two, we've got a wire that connects the 2 electrodes, the bits of metal, and then we've got a salt bridge which allows for passage of ions through to both solutions, from one solution to the other. So that's the setup, and that's called a galvanic cell. And the electrons that run through that wire can do work just like a regular battery can. All right, does anybody have any questions about the setup so far? All right. Sorry, I'm just going to try and move this here. No, it doesn't matter, I don't think. Okay. So when you're starting off with something like this, it would be necessary to know what the electrode potentials are for zinc and the cadmium. So the two reactions you'd be looking for on the reduction potential table would look like this. Now I know this because I can see that the cadmium is 2+, it needs 2 electrons to become cadmium solid. And likewise, the zinc 2+ needs 2 electrons to become zinc. So what I'd be doing is trying to hunt these reactions down on the reduction potential table.
Can I ask a question, please?
Yeah, yes, Madonna.
Where is the, I don't see the zinc 2+ that you put, I made the equation out of.
Do you see the zinc here? The zinc.
Oh, okay. So that 2, okay.
Right. Well, that's, you know that nitrate NO3, well, actually, you can even see it down here. See that? Zinc 2+.
Oh, yeah.
CD 2+.
Sorry.
Right. And
Yeah,
those are going to be the solutions. See, these things are
Okay.
always in solutions of their metal ions every single time.
Okay, thank you.
The number of electrons we add is always equal to the charge. So if it's 3+, it'd be 3. If it was 4+, it'd be 4, etc.
Okay, thank you.
I need to get the reduction potential table here, so I'll go ahead and find that.
For our test, how will we have access to that table?
You won't need it, Rebecca.
Great.
And
Thank
I'll,
you.
I'll explain why. I'll explain why you won't need it in a little bit.
Okay.
But it's the same. It's really the same kind of thing. And to get practice at doing this, I'd recommend doing some of the fun quizzes. All right, so here we go. Zinc 2+ gives zinc. That's going to be minus 0.763 volts. And the cadmium here, minus 0.403 volts. So it is 0.03 here. Okay, so that's what we have. Now, in order for this thing to be actually working, and it does say here, this cell may or may not obey the conventions of a standard cell diagram. What that means is a standard cell diagram is always going to, by convention, have the anode on the left and the cathode on the right. What I'm saying is that that's not necessarily the case here. So that's the first thing. Secondly, you're assuming that the cell is working spontaneously. What that means is that it must be creating a voltage. And the only way it can create a voltage is if that voltage is positive. So the idea here is you look at the two voltages you've got here and you ask yourself this question: which one of these has to flip around in order to make it so that when you add these together, you get a positive value, a plus voltage? And as a general rule, you always know that you're always going to flip the smaller of the two numerical values. So if I did that, this is how I'd end up. See, this is one of the rules of voltages, is that if you flip it around, you change the sign.
Oh.
And you can see, I don't really care about what the sum is here, but when I add them together, I know I'm going to get a positive value. And the rest of it's going to be like this. So that's my process right there. So the first step there is to look at the two and figure out, well, which one do you have to flip? Well, you flip whichever one you have to flip in order to make it so that when you add them together, you get a positive value for, this is what we call the E0 cell, which is the cell voltage. That's the actual voltage that would register on a voltmeter if it was in this wire.
Do you always add the E0 cells? Is there every time you subtract? I think I feel a little confused because in the lab there were two possible equations
Right.
for E0 cell.
Yeah, you see, the thing is, here's how it worked out in the lab. You could do whatever it took to, you'd flip one, which would mean you'd have to, so this would be, these are reductions, right? They're both reductions. So you'd have to subtract one of the reductions that turned into an oxidation, or you flip one, turn it into an oxidation, and you add them together.
Okay.
So, I mean, if you think of it that way, it's not really, I understand, I get what you're saying, that it is kind of confusing, but it all depends on when you're doing the flip, or if you're flipping at all. If you're not flipping, then you have to subtract. If you are flipping, then you have to add. But if you've added, then you've already flipped, which has changed the sign anyway.
Okay. So it is essentially the same thing, but
yeah.
two different ways of getting there.
That's exactly right.
Okay.
It's kind of like minus and plus negative. Think of it like that.
Right.
You're really the same thing, but yeah. All right, so what I like to do for these is I like to do a little bit of labeling and get an idea of what's happening on each side. And I can tell from the top one that we're dealing with an oxidation. I also know that it's dissolving. I'll explain that in a second. And I also know that it's the anode. Okay, let's talk about the dissolving part first. If I've got zinc solid and it's turning into zinc 2+, that means the solid is disintegrating. So it's dissolving. I think that's handy to know. That can help with a couple of these questions. The whole oxidation anode, that's one of the conventions. Oxidation occurs at the anode, reduction occurs at the cathode. You can remember that. R and C are both consonants, O and A are both vowels. So oxidation, anode, reduction, cathode. The other thing is that the electrons are on the product side, which makes an oxidation as well. Any questions? The other one is yeah.
Like, so we can say the reduction, it's just forming into a solid, right?
That's right. Yeah. So I would say plating, reduction, plating.
Plating.
Yeah. And cathode. Now, what I mean by plating, you've heard the term electroplating, right, Adam?
First time hearing it.
Oh, okay. Well, the idea is that I told you the zinc is dissolving, right? So if you were looking at this, you'd actually see this electrode that I'm pointing at here. You'd actually see that physically dissolving, actually getting pock marks and holes and everything in it, disintegrating. Right. On the other side, what you'll find is cadmium will begin to coat onto this. This will get visually thicker.
Right.
As cadmium coats on it, or plates onto that electrode.
Yeah.
So you'll see that electrode thickening up, which is plating is a term for that.
Okay.
When you're doing your essays, electroplating, I think, is one of the topics. So take a look.
Interesting. So, like, say if like the battery just starts, I mean, like, there's just no more juice left in it. There's no more voltage left in it. The anode, which is the negative sign of the battery, it just starts to corrode because it's just pumping out as much as it can, but there's like no voltage, so it just starts going up to the top. Or
no. As it's forming electricity, the zinc is actually dissolving. So once the zinc is gone,
Yeah.
the battery's dead.
Okay.
Yeah, I mean, the solid will have all turned into zinc 2+, which means it's all solution now.
Right.
So the same. Go on.
Go ahead.
Go on, Adam.
All right. So let's like all right, so like let's put it in a reality perspective. Like I open my hood of the car, and there's just corrosion everywhere on the negative side of the battery, which is the anode. That's like basically just the zinc dissolving as much as it can, but like, is there like anything on the cathode that's like not taking that voltage? Is there just too much plating happening on the cathode?
Well, I don't know if you can have too much plating. All I can tell you is once the anode's used up, the battery's dead.
Yeah. Okay. Yeah.
And what you're seeing on a car battery is something a little bit different. I think there's a side reaction going on that causes that kind of stuff that occurs on the electrodes. The other danger, I know there's a definite side reaction that can occur with some lead acid batteries, where the H+ can turn into hydrogen gas, which can be kind of dangerous. And stories of lead acid batteries exploding because of hydrogen being formed.
Duralast.
All right. Anybody got any questions so far about what I've put on these reactions so far? All right. The next thing we can look at is what happens in each case here. So we've got the species being oxidized. The species being oxidized is going to be the zinc, because the zinc is turning into zinc 2+, and you can see the electrons over here. That's why I put oxidation here. So the answer there would be W, and that's why W is the answer here. Let's do the next one. The anode and the cathode. The anode is the one where oxidation is occurring. So we know that it's the electrode, it's a piece of metal that's stuck in here. But in this case, it's going to be the zinc. So the answer there is W as well. Anybody got any questions so far? I'm going to skip. Go on. Sorry.
Sorry. So the species being oxidized and the anode are the same, and then
Yes.
the species being reduced and the cathode are the same.
No. Yes on the first question, no on the second.
Okay.
I'm going to hold up on that though. Okay. We'll get to that in a second.
So as like reduction occurs, that's just where the plating comes in, right?
That's right.
More plating.
Mm-hmm.
All right.
Yeah. But Miriam, I will get to that question in a second and explain why I said what I said. Let's see the next one. I'm going to skip over oxidizing agent for now and reducing agent. We'll get to those in a second. The next one says direction of flow of zinc 2+. So what we're looking at here is zinc is turning into zinc 2+, which means it's dissolving. The zinc is on this side, so the answer would be F, and it's dissolving, so the arrow is going away from it. If it was plating, it would be E, but since it's dissolving, it's F. Any questions? The cathode is the other electrode, the one where plating is occurring, and that's going to be the cadmium. So that's going to be Z, not Y, but Z. The species being reduced. Well, this is what I was saying earlier, Miriam. The cadmium 2+ is being reduced to cadmium. So cadmium 2+ is the species being reduced, and that's going to be Y.
Oh, okay.
So that's why I said what I said.
The solution is being reduced, correct?
That's correct. And that's the thing with these batteries is that something is always being oxidized, something's always being reduced, something's always dissolving, and something's always plating. The reducing agent. Sorry, go on.
This is like a kind of like an off question, but do we specifically use alkaline earth metals for batteries because it's a +2?
Generally, well, you know what? I've never heard of that. I know of lithium batteries, but that's a
Lithium batteries,
that's an alkali metal though. Yeah, so I don't know. I don't know of any magnesium batteries or beryllium batteries.
Calcium batteries.
No, I've never heard of that. But I have heard of lithium batteries, so that would be an alkali metal, not an alkaline earth metal.
Right. Okay, so transmission metals or transition metals would work better for voltage, I suppose.
Well, no, actually, as far as voltage goes, you've got to be looking at the differences that would occur when you're looking at the table here. So, you know, you're looking at the difference between the oxidation and the reduction to see if you can get the maximum voltage, if that's what your aim is. You'll find that lithium would provide that if you look at the tables.
Hmm.
All right, the next one, we've got, I was going to skip over reducing agent. I'll get to that in a second. The flow of CD2+. Now, CD2+ is turning into cadmium, which means it's plating, and that's on this side. So that's why the answer would be G. And then the last two, we've got direction of flow of nitrate and the direction of electron flow. Well, the electrons are always going to be flowing in the wire, so the answer can only be A or B for that. And the direction of electron flow here would be B. B, because the zinc is turning into zinc 2+ plus 2 electrons, and then the cadmium 2+ is accepting those 2 electrons. So the electrons must be traveling through the wire over from this direction over to here. Now the nitrate travels through the salt bridge, because what's happening here is the zinc is turning into zinc 2+, which means that the zinc 2+ needs nitrates to balance it. And the cadmium 2+ is turning into cadmium, which means we're losing cadmium 2+, which means that this doesn't need nitrates anymore. So the nitrates are actually going to flow from this side over to this side. So the answer is going to be C. What you'll notice is that the nitrates and the electrons always flow in the opposite directions, which makes sense because nitrates are negative, electrons are negative. You can't have the negatives traveling in the same direction. So that's a very quick and dirty explanation for this, but I strongly recommend you watch the videos where I explain this in detail as to what's going on. Does anybody have any questions? Oh, no, sorry. We've got to talk about oxidizing and reducing agents. So,
So reducing agent, that's we're just only talking about the zinc instead of just it being the oxidizing, right? Oh, yeah, nice.
okay, it sort of flips around. When I'm using the word agent, it's in the context of it being a cause of something. So if you've got something being reduced, what's being reduced here is the cadmium 2+. Why is it being reduced? Well, it's being reduced because it's accepting 2 electrons. Where's it getting the electrons from? Well, it's getting electrons from the zinc. The zinc is supplying the electrons, which makes it the reducing agent. The zinc is supplying the electrons, which makes it the reducing agent. But the zinc is being oxidized. Now, the species being reduced here is causing the oxidation of the zinc. Likewise, the species being oxidized is causing the reduction of the cadmium 2+. So the result is that whatever's being reduced is the oxidizing agent. Whatever's being oxidized is the reducing agent. I know it sounds confusing. That's why I left it to the end, but that's what we call them. All right. Anybody got any questions?
Yeah, that makes sense.
Okay, that's good. All right, let's take a look at the test here. And you can see the way I handle it actually makes it a little bit easier than what it is on the regular test. So Rebecca, you were asking how you'd have access to the table. Well, you don't really need it because I give you this information down here. Instead of W, X, Y, and Z, I've got I, J, K, and L because they fit nicely into the alphabetization to make this a bit easier. And the way you handle this is these are, again, fictitious. So we don't need any other information. But here's what we're told. We're told the reduction potential for Q plus is minus 0.9 volts. What that means is it looks like this. And for R plus,
Wait, what are we talking about on this? Or?
well, did you see the reduction potentials here, Adam? Q plus and R plus?
Yeah.
And the way you know to set this up is because it says they're reduction potentials, which means they need to be set up as reductions, which means the electrons have to be on the reactant side. That's how we know to set them up this way.
So, I mean, for this point, I mean, like, don't we need one minus and then one positive?
No, no. At this point, we need to know which one of these we have to flip in order to get a positive E0 cell.
No. Flip the negative sign, or flip the negative sign.
That's right. It's always the smaller of the two, and negative 0.9 is smaller than 0.2.
Right.
So if we do that, we get this. Q gives Q plus an electron. That'd be 0.900 volts, and the other one stays the same. So there you go. That gives a positive value, and there's our situation. R plus Q gives Q plus R. Now we can do the same thing as I did earlier. The Q going to the Q plus an electron, that's going to be the oxidation. It's going to be the anode, and I know it's going to be dissolving. And the other one is the cathode. It's a reduction, and it's going to be plating.
So the reduction potential that gets flipped is always the anode?
Yes, that's true, Nathan. That would be true.
Oh, okay, thank you.
All right, so then it's really just the same questions as we asked earlier. Direction of nitrate flow. Well, the nitrate's going to flow from Well, it's either going to be C or D. We know that. But the nitrate here is going to flow from the side that has the R plus to the side that has the Q plus. And that would be, well, the R is the L and the K section over here. So we know that the nitrate will flow from this side over to this side. So the answer there should be C.
That's because the R plus is in the reactant side, right?
Yeah, well, the R plus is turning into R, so it doesn't need nitrates anymore. The Q is turning into Q plus, which means it needs nitrates to balance it out.
Okay.
So it's going to travel from the R side to the Q side. The R side is this side, and the Q side is this side.
Mm-hmm.
We know that from over here. Do you see that, Adam?
Yeah.
Okay. Oxidizing agent. Well, the species being reduced is the oxidizing agent, and species being reduced is R plus. And R plus is going to be K. And K is going to be 11, so it goes in here. Species being oxidized is the Q. And Q is going to be the I here, which is going to be 9. The species being reduced is R plus. R plus is going to be 11. You'll notice that the oxidizing agent and species being reduced and the species being oxidized and the reducing agent are always going to be the same. Well, not the same as each other, but you see the oxidizing agent, species being reduced to 11 and 11. They're always going to be the same. Direction of electron flow. Well, the electrons are flowing from the Q side to the R side, which means it's going to be direction B. That's number 2. The anode, that's where oxidation is occurring. That's going to be I. The reducing agent, well, that's the same as the species being oxidized, so that's number 9. See? You just make them the same. Direction of flow of R plus. What's R plus doing? R plus is plating. So that's going to be G, which is going to be 7. And the cathode. The cathode is where reduction's occurring. That's the R, so that's going to be L. So that's going to be 12. And direction of flow of Q plus, Q is dissolving. So that's going to be F. There you go. The answers aren't always going to be the same because it depends on which side's the anode, which side's the cathode. So that's why you can't just write down what you think the answers are going to be and just say, well, it's going to be for all of them. You're going to have to do a little bit of thinking at least. Although I tell you what, having the notes for something like this, having the page of notes, it just makes this, I think, a bit too easy myself. But you know, whatever. Does anybody have any questions? Anybody got any questions?
Not about this. Like, I'm good with this. I do have a question about another topic, so I'll just wait if everyone else.
Okay. All right. Does anybody have any other questions about this or the redox reactions? All right. Okay. So, Miriam, was it you who had the question?
Yes.
Okay. So I will. I'll stop the screen share now, and if everybody's done with the other stuff, and we'll just anybody can hang around if they want. Actually, I'll stop recording is what I'll do. So what I meant to do. I'll stop the recording.